my cue to start, isn't it? So let's get started. How's everyone doing?
Great.
Wonderful? Making it? Yeah, I understand that one. Yeah, so anyway, it's the beginning of the semester, so you can't be too far behind yet, right? Isn't that one good way of looking at it? Okay. At least that's what I keep telling myself, okay. So, we've been doing NMR, as it must seem like we've been doing it forever now, doesn't it? Okay, but did anyone work on that one? I think we ended here last time. And remember, the first thing we do is what? Very good. So, are there any? No? Okay, so that's always good. And how many hydrogen environments are there? Two, okay. And we have a quartet and a triplet. Is that speaking to anyone?
Ethyl.
An ethyl group, okay. But we have 4 carbons. How can that be? Something else we look at is that, tell me. Oh, wait a minute, never mind. There we go. Something else we have is that this one here is over close to the 4, around 3.5. What's that say? What's that? Yeah, and so what in our formula is electronegative?
Oxygen.
So in other words, these protons here are the ethyl, so that would be what, the CH2. Okay, so we've gotten pretty close. First time I've had a brown one here. Those other ones, I don't think. So we've got an O and a CH2 and a CH3. That is a 3. Okay. Well, we've got it all covered. The only problem is it doesn't match our formula. So what do we got to do? How can we make it work? What's that, Alex? We can, can't we? Because then, if we do that, how many proton environments are there in this? 2. Okay. Because these are the same and these are the same. Now what's our integration ratio? 2 to 3 or 1 to 1.5. I mean, that still gets me. But anyway, okay. And so it fits. Any questions on that? I wish they were all that easy, right? Okay. Okay, so now we're into the thing that Al loves to just, I don't know. You know, you said it was going, I know that's got 2 proton environments, what difference does it make? But anyway, for some people, for some of these, it's really good to know to apply these possibilities, okay? Especially when we're dealing with chiral molecules. So let's look at this part. We have to realize that we need to look at the electronically non-equivalent hydrogens. Now, so far it's been pretty straightforward, but there's times when it's not. So a lot of times we can look at it and say, oh, well, that has 3 proton environments, or like this one, oh, that has 2 proton environments. But one way of doing that, because when we get to chiral molecules, it makes it a little bit more difficult, is to replace one of the hydrogens with an X and see if replacing it in different places would make a difference. So there are 4 different ways we can do this. Okay, our first is totally unrelated. So what are we saying as far as unrelated? Well, the blue, are the blue related to the green? In other words, if we put an X here or an X here, would it give us the same compound? And the answer is no. Okay, it wouldn't. So that's what we're saying. So these are unrelated. Now if we put an X here or an X here or an X here or here or here or here, it'd be the same compound, wouldn't it? But if we put one, if we put one at a blue and we put one with a where the green are, we would have two different compounds. We would have isomers, constitutional isomers. The second one is called homotopic. And when we're dealing with that, again, this is what we were saying. This would be the same, wouldn't it? Doesn't matter which one of these blue hydrogens we replace with an X, it would give us the same compound. And so in this case, it's giving us something that's identical. And rather than calling it identical, we're going to call it homotopic. Okay? Got to learn another good word, right? Okay. Then we have enantiotopic, and this one gets kind of interesting. It's really homotopic, but we're going to call it enantiotopic, okay? Because we look at this and we say, well, wait a minute, this one's pro-S and this one's pro-R. Everyone remember what pro-S and pro-R it means? It means that if we were to replace this with an X, then we would end up with an S. It would make this a chiral carbon, wouldn't it? Okay, everyone see that? If we put some group on here, like a halogen or something, or it would make this now 4 different things bonded to this carbon, and so we'd have a chiral carbon. And if we put it here, it would make it an S, and if we put it here, it would make it an R. But the thing is that without it, these are equivalent, aren't they? Without that, they're equivalent. So we're going to call it an enantiotopic, but really, because it's not making a chiral center, we're not actually doing it. Without doing that, they are equivalent, and so so we're going to call it an enantiotopic, okay? And we will get the same. These will be identified as the same peak in the NMR, okay? Everyone understand that one okay? All right, so we would only get 1 peak for this. Might be split, but we'll only get 1 peak for this, for the enantiotopic ones. And then the final one, and this is the one that's kind of confusing in some ways, but we have to realize that once we have a chiral carbon, it affects the molecule, doesn't it? Okay? And so diastereotopic, what it's saying is that because of that, if we substitute here one of these two, yes, we have pro-S and pro-R, but the thing is that they're already different because we have a chiral carbon right here. Okay? And what it's saying is that this is going to see this differently and this is going to see this differently if as far as the hydrogens go. So they will have different NMR absorptions, and we're going to call that diastereotopic. That also, and this is the thing that you have to remember is when you get into AL is cis-trans also falls under the heading of diastereotopic. Okay, so when you're doing your AL and it's saying, is it unrelated, homotopic, and antiotopic, or diastereotopic, if it's cis-trans, call it diastereotopic, okay? Because cis and trans we know makes a difference too, doesn't it? Okay. So let's look at this problem, and I think it'll help make things a little more clear as far as what we're talking about here. And it says identify the indicated sets of protons as unrelated, homotopic, antiotopic, or diastereotopic. So what is A? Delaney, you got it? You don't think so? Okay, well. Would that be pro-R and pro-S there? Everyone see that? Is there another chiral carbon on that molecule? There isn't. So what is it? were saying it. I knew you had it.
That might be wrong.
Okay, how about on this one, B? Well, we're showing these two hydrogens. Are they pro-R or pro-S? We replaced one with a halogen. Would it make it chiral? It'd make it 4 different things, wouldn't it? Okay, so that narrows us down. It can be an antiotopic or it can be diastereotopic. Now, is there a chiral carbon on there? There is, isn't there? Chiral carbon right there, right? 4 different groups on it. So what is it? Okay. We're doing good. How about this one?
Homotopic.
Are these 2 methyl groups identical? Do we have one that's cis to another methyl group and another that's trans to another methyl group? So let's see what we've got. This is diastereotopic, okay? This is what I was talking about, cis and trans. This one here is cis to this methyl group, and this one here is trans to it. And so they have different environments. And so this is the cis-trans of diastereotopic. Okay? Everyone understand that now, I hope? Okay, let's try the next one. Anybody gonna be brave? Well, let's see. Thank you for being brave, and you were right. Okay, very good. All right, when we're looking at it, yeah, why is it diastereotopic? Well, this would make a difference. One would be pro-R and pro-S for one. That's the first thing we look at. And after we establish if one would make pro-R and the other pro-S, in other words, if we replaced one and make a chiral center, it'd have 4 different things on it. Then we go and we look and see, okay, is it an antiotopic or is it diastereotopic? Well, we have what's this carbon right here? Chiral, isn't it? And so it's diastereotopic. Okay. Anyone? It's diastereotopic. Why is that? Right? Well, the main thing is it just has a chiral center right here. So that's going to make it diastereotopic. Okay. If we put one here, then that of course would do the same thing, wouldn't it? Because that would make this carbon now different than this. There's a hydrogen there, and so it would also make it. So we have both things. So we have the enantiotopic with that, but then since we have a chiral center here, it makes it diastereotopic, okay, instead of enantiotopic. And finally, what's this one here? it, Abby? Would it make a difference if we put an X here or if we put an X there? Are there any chiral carbons on that? You want to venture a guess? Homotopic. They are related, but they are, it's not unrelated, so they are related, so we're going to call it homotopic. Okay? Are you getting a little better idea about this? Okay. Owl strengthen or drive you nuts, one or the other, I don't know. Okay. How many absorptions would S malate, an intermediate in carbohydrate metabolism, have in its proton NMR spectrum? Explain. The ivory ones are hydrogens. Oh, what is this molecule of the four? Is there a chiral carbon there?
Mhm.
There is a chiral carbon, okay? So, there's our chiral carbon. So how many different proton environments do we have in this? Are these going to be identical? No. So how many, Alex? 4? Everything's going to be different. It's going to be diastereotopic because we have this chiral center here. So we will have 4 different ones. Okay? Stereochemistry gets you every time. Okay, now we're going to get into what you normally get, which is all this mess here. Okay? This is toluene. And what we have here, I mean, this is easy. This is this one, okay? But here's our aromatic ring. And the main thing we really need to look at, it's showing it looking like this, is we just look at the integration of this whole thing. And this is 3 to 3 to 2. And so this is the aromatic portion, so that's 5, right? 3 and 2 is 5. And normally you just circle it and say aromatic, multiplet, and let it go. Okay? I mean, normally that's what you're going to do. That's all I'm going to expect you to do. Okay? But instead what we're seeing, and in a lot of instruments, you would just see this as one peak if it didn't have very good resolution. You'd see one big peak here, and you'd look at the integration and say, okay, aromatic, multiple, aromatic. But instead we get this mess. Here's another more complex one. And this trans-cinnamaldehyde smells really good. It smells like cinnamon. So anyway, when we're looking at this, this one's very easy. We immediately know it's what, just by its location? Aldehyde, okay? And it's split into a doublet because it's being split by this hydrogen here, right? So we got that one down. Okay, but we have to look over here. So this is 1, and so that means that these must be right because this is 1 here. All right? And now the question is that when we look over at this one, wait a minute, what in the world is that? It sure doesn't look like the quartet we're used to, right? And then we can see that we would have 1 here, and we would have a multiplet, an aromatic multiplet here. Now, the problem is that when we look at this, if we looked at it and we didn't have this nice green pointed out to us, we'd look at this mess, we'd circle it, say aromatic multiplet, and be done with it. But we can't do that because if we did that, we would add 3 and 1 and 2, giving us 6. And there's no way it's 6 aromatic protons, right? And what we see in this that makes it so interesting is that if you look at it, here's your aromatic ring. This hydrogen is in conjugation with the aromatic ring. It's benzylic, isn't it? In fact, we have a lot of conjugation here. And that conjugation is shifting this up over here into the aromatic region. And because it's, you know, we've got a lot of things that can go on in there, and we can have resonance structures around there. And so what we see is that what we have is in here is a doublet. This one being split by this one here. Okay? It's just, the fact is it got shifted in with all this normal aromatic mess. But this one's being split by this one. Okay, so now that's easily explained. All the rest of this we'll just say is our aromatic multiplet with this one here, our benzylic proton in there, intermingled with them. But then we have this right here we've got to explain. Well, that's this hydrogen here. It's being split by this one, and it's being split by this one. So we'd say, okay, it's being split by 2, so we should have a triplet, right? When these come from different environments, I mean, this is on an aldehyde, this is benzylic, what we see is something called a split of a split. How's that? Okay, to make things complicated. So what happens is that we will see that this will first be split by one, and then those splits will be split by the other. And that's why we get something that looks like that instead of our typical type of thing. So here's our proton on C2, and first it's being split by 2 and 3. In other words, first it's being split by this hydrogen here. These are trans. We know that they have a little bit larger J coupling. So first it's going to be split here, and then this aldehyde one is going to split this one. So the first thing we see is a doublet, and then that doublet is being split by, each side of it's being split by this one. So we have one here and one here. So it's a split of a split. Okay? And that's how we get that. And remember, doublets are typically pretty even. Now, there's a little bit of change there, but that typically happens. Well, let's look at this one here, worked example. It says 3 bromo, 1 phenyl, 1 propene shows a complex NMR spectrum. Well, that looks kind of similar to what we had before, doesn't it? Only now we have a CH2 here and a bromine, so that's going to make a difference, isn't it? So when we're looking at it, it's, as we would expect, this one here is going to be split by these, and it's going to be split by these. So it's going to be split by both. So it says draw a tree diagram for this one here and account for the fact that what you end up with is a 5-line multiplet. How in the world are we going to get 5 lines? Well, remember we got 2 over here. So 2 is going to split this one into what? A triplet. Okay? And this one's going to split it into a doublet. Okay, I'm going to go ahead and show this to you. So what we see when we're looking at it is our 1, 2, our 1, 2, this one here, first splits it into a doublet. So first we get our doublet. Then what we see is that this one, this side split into a triplet, 1, 2, 3. And this side split into a triplet, 1, 2, 3, but these 2 come together in the middle, and that gives us this type of interesting pattern. Okay, so they are, you can explain them, okay, and they're typically done by this tree type thing. You won't generally have to go into that so much. You could try doing that with your unknown if you get an unknown that you're trying to explain everything out with or something, but, or some things in lab, but typically you don't have to worry about it too much. You kind of just figure that's a split of some sort. You can have things where they're so similar that they behave where you can have have something on this side and something on this side, and they're so similar that you can just add the protons and get it, okay? Sometimes that happens. But if they're dissimilar, like these two examples we showed you, you'll usually get splits of splits. A split of a split. Okay, so now, we've been talking about how great NMR is. You're gonna find out even more so. How do you know you made your product? You know, you gotta identify it, don't you? So NMR can be used to do that. So here we have hydroboration oxidation, all from last semester. Is it Markovnikov or non-Markovnikov? What would you expect to get with hydroboration oxidation? What? Non-Markovnikov. And so that would mean, where would our OH go? Would we have cyclohexylmethanol or 1-methylcyclohexanol? First one or second one? One on the left or one on the right? It's non-Markovnikov.
Left.
The one on the left? That's what we would expect, isn't it? Because it's going to be, Markovnikov would put it on the more highly substituted one, which would be right here, wouldn't it? But this is non-Markovnikov because it goes up as a whole when it's doing it, so it needs the least sterics, and so we would expect it to go here. So this is what we would expect. So now, how do we check and see if we're right? NMR, right? Check by NMR. Okay, so let's see what these things look like. All right. So we have these two possible products, this being the Markovnikov, this being the non-Markovnikov, this being the Markovnikov. And what we see is this is the expected one. Do you see a difference here? Major difference, major difference, okay? And why is that? Why is it so much different? Well, these are all so close together, it's just one huge mess here. I mean, that's what it comes down to, it's just a huge mess. And plus we have an OH in there. But all of these are gonna be so close together, we're just gonna pretty much have a mess. But when we do this one is going to make it stand out, isn't it? Because now these hydrogens are directly next to an OH, aren't they? This carbon's bonded to an OH. That's going to shift them down this way. And so this is what we would be looking for. We'd be looking for this. Any questions on that? How can a proton NMR be used to determine the regiochemistry of electrophilic addition to alkenes? Okay, and so really what it's asking is for you to determine whether the addition of HCl to 1-methylcyclohexene yields 1-chloro-1-methylcyclohexane or 1-chloro-2-methylcyclohexane. Well, is this Markovnikov or non-Markovnikov? What is it? It is. It's Markovnikov. So which of these products would you expect? The one on the left or the one on the right? The one on the left because it's going to go to the more highly substituted one. Okay, so you're saying that we should expect this one, okay? Now how are we going to determine the difference between these two? Just looking at it, what would you look for in your proton NMR to determine the differences? First off, is there going to be a different number of proton environments between the two?
Yeah.
There are, aren't there? Because this one, these two will be the same, won't they? And these two would be the same, and then there would be this one here. When we're dealing with this one, we can't say that, could we? They're going to be all different. These two would not be the same, neither would those two be the same, would they? Okay? So we're going to see a different number of environments for one. Is there going to be different split patterns too? let's just kind of look at this. Okay, so you would expect that one, okay? And what we would see is that this one right here, these right here are not going to be split, are they? Okay. Will these be split? Yeah, there's a hydrogen on this carbon. Okay. But this won't be split. So that's one of the first things we look for, okay? Plus, this one that's not going to be split, it's on a carbon bonded to chloral group, so it's going to be more de-shielded, isn't it? So this is what we see. And I went into ChemDraw and I drew this, just trying to get you to understand when you're doing this homework on this. You've got a wonderful resource in this $2,000 program you can just download and use, okay? You can draw it up so quickly and then just have them predict these, and you can see where things will be if you're struggling with it or anything else. In fact, when you're doing this, I'd have ChemDraw up and ready to go. Okay, it'll save you time. How many of you like saving time? I like saving time, okay? And so when we're looking at it, this is what this is predicting. Now, why are these different here? They're not really all the same, are they? Now we're dealing in cis and trans things, aren't we? Because we have a ring. One of those hydrogens will be cis and one will be trans to the fluoro group. Okay? And so same here when we're dealing with it. We will have one cis and one trans. And so they will be different. Finally, we're into C13. Any questions on proton before we go on to C13? Or anything we've studied? You starting to get it down a little bit? Gets pretty complex, doesn't it, when it's all said and done. And trying to figure out what structure you have, it takes time, okay? You have to really think everything through. So, okay, we know carbon-13 is the only naturally occurring carbon isotope. I mean, carbon-14 won't happen. There's very little of it anyway. And carbon-12 won't work. And so, but it only, it's the only naturally occurring carbon isotope. And so it's only 1.1%. So when we're dealing with this one, we have to use, and we're using NMR, we use something called an Fourier transformed NMR, okay? And the thing about that is it helps in detecting it. And we've gone through this in lab. Some of you have, some of you haven't yet, okay? And so what we see, I always include it in both lab and lecture. It doesn't hurt to see it twice. But because there's so little of it, we can't get as much information out of it, for one. And then we can't do integration, and we can't do splitting and that. But the other thing is that we have to put more sample in if we can. And even if we can't, or even if we don't want to waste our sample or something, we take a lot of scans. And so by taking lots of scans, those in my class, my lab, what did I say about noise and signal?
Noise is random, signal is not.
Noise is random, signal is not. Keep that in mind. Noise is random, signal is not. You were paying attention. Good. Okay. Looking at this, we don't know if that's a peak or not. We don't know if this one over here is a peak. I mean, we have no idea. That one may or may not be. I mean, who knows? But if we take more and more and more scans, then what happens is the noise will cancel itself out as we average them out, and the signals will continue to increase. This still, as far as I'm concerned, needs more scans than 200, okay? But now we definitely know this wasn't a peak, this wasn't a peak, this wasn't a peak. I mean, there was no way really to know until we took more scans. I'll get over here. So when we're dealing with it, we do it so that we're not going to see carbon-carbon splitting each other because there's so few C13s in there that to have too close, you know, to be able to always do splitting and stuff, it's just not going to happen. And we can see hydrogen coupling, but we don't do it because we use something called broadband decoupling method. So when you see something that asks on this broadband, everyone listen to me on this one, on this broadband decoupled spectrum, just think it's a normal routine C13 NMR, okay? It's just the normal one. They just put that on there because what they do is they get rid of what can happen. You can get hydrogen coupling, and they get rid of that. They keep the hydrogens going back and forth so that it doesn't have a chance to couple with, as a separate signal, it doesn't have a chance to couple with any of the carbons. Okay, so what can we get then? We can get the number of carbon environments, and we get a general idea of what kind of environment they're in. That's all we're going to do. Much simpler, isn't it? Much simpler. Yeah, it is. It's much simpler. Okay? So here we have an ester here. And let's look at this and what we see. Well, how many different carbon environments are there? Well, there's 4 carbons, and they're each in a different environment, aren't they? Everyone see that all right? Yeah, they're each in a different environment. And we have a carbonyl, and the carbonyls are down in this region here. And we have one directly bonded to an oxygen, so it's going to be over in this electronegative region. Now we're going to learn that carbonyls that are from carboxylic acid derivatives, they're going to be from here over to about here, and aldehydes and ketones are going to be up over this way. Okay? So we know that this one, this carbon here is going to be this one. We know this carbon here is going to be this one here. This one's next to a carbonyl, so it's going to be that one, and then this one, the methyl's going to be way over there. So general factors that determine the chemical shifts include the electronegativity, which we just saw, right? We're going to talk about the diamagnetic anisotropy. I have a hard time saying that one. Anisotropy of pi systems, in other words, non-uniformity, and the absorption of where sp3 is in comparison to sp2. So when we're looking at here, this is our sp3 and here's our sp2. So when you're looking at it, if there's only just hydrocarbons there, the sp3 will be more shielded than the sp2 if you're trying to figure out what goes where, okay? And then the sp, or the CHs, are going to be, well, the CH3, the primary are going to be here, the secondary will be here, and the tertiary will be here. Your halogens, it depends on how more electronegative they are than the others. So in other words, your fluorol groups would go more over here, and your bromo or iodo would be more down here. Then your nitrogen, and then your oxygen is more this way. And look at this. Here's our triple bonds here. So they're still kind of out there a little bit. But now we have nitriles. We didn't worry about nitriles with proton anymore. Why not? Why didn't we talk about nitriles with proton anymore? No hydrogens, yeah. So when we get something in this region, we also, in proton NMR, generally, not always, everything's always general, the alkenes were more shielded than the aromatics, weren't they? But notice here, nitriles, aromatics, and alkenes are all in the same general region. Okay? And then our carbonyls are up over here. So that's not that much to remember, is it? Basically, you have your hydrocarbons, your electronegative or triple bonds, your alkynes, you've got your nitriles, aromatics, and alkenes, and then your carbonyls here. Okay. This is trying to explain that one about the pi system. And so, what we see is that we mentioned in lab, those of you who are in lab, the protons are de-shielded because of this induced field. We have these circulating electrons, which makes this induced magnetic field, which puts them in a shielded area, a de-shielded area. De-shielded area. Notice the carbons are in a de-shielded area as well. The only way to get something in a shielded area is if this hydrogen was pointing inward, which it's not. Okay. So here let's look at 2-butanone. And everyone remember what this does? It means that we have to take this and put it here. Because we're only going to go to 200, but we have something at 208. So the only thing we can do is put it like this and say what its number is. Okay, that's all that is. Okay, now notice this is a ketone. So ketones are more down here, aren't they? I'm saying that. Okay, what else do we have here? Well, we have this one here and we have this one here that are both CH3s. Okay, they're both CH3s. So, but this one is next to a carbonyl. So that one and this one's next to a carbonyl. But this is a CH2 next to a carbonyl. This is a CH3 next to a carbonyl. Okay? Everyone see that? So the CH2 is going to be this one, and the CH3 is going to be this one, and this one's a couple of carbons over, so it's going to be that one. Here's parabromacetophenone. Okay, here we have how many different, we have, when we're looking at it, this is a ketone. It's in conjugation, it's actually lowering it down to here. Okay, so it's here. It's still in the aldehyde or ketone region. This is our aromatic region. And we can see that these are the same and these are the same environment. So we have 1, 2, 3, 4 different, aromatic environments. Is this twice the size of this? It's not, is it? It doesn't have twice. This has more than twice the area of this. So again, we don't do integration. We cannot do integration. It depends on how it's held and its relaxation. Okay? So, but we can see that we have 4 aromatic carbon environments. And then, of course, we have this one down here. Ethylbenzene. Okay, we got all this. This is where we're going with it. Here's ethylbenzene. What kind of carbonyl is that one? What's our functional group?
Ester.
Ester, and so it falls within the aldehyde ketone or the carboxylic acid derivative ones. Carboxylic acid derivative, so it's going to be over, when we're talking about it, it's going to be over in this region here, and that's what we're seeing. Okay, about 168 or so. Here's our aromatic, and how many different carbon environments do we have in the aromatic? Well, we have 1, 2, 3, 4. Word to the wise. In protons, we would say, oh, we wouldn't count that, would we? And I can't tell you how many students get messed up and forget to count it for carbons, because they're used to not counting it for protons. Can you see yourself doing that? Okay? So you gotta count it for carbon, but you don't count it for proton. So we're gonna have 1, 2, 3, 4, and that's what we see, 1, 2, 3, 4. And then we're gonna have the CH2 that's next to the oxygen for the electronegative atom, and then the CH3 down at the end. Any questions on that? Okay. Worked example. Classify the resonance in the C13 spectrum of methylpropionate. What are they? What's what? I've got this. If somebody wants me to tell me what one of those are, you can point it with the laser pointer. Who wants to volunteer? You're going to?
Yeah,
all right.
Sure. Is that one the CH3
Three.
right there?
Uh-huh.
Yeah, that one right there.
remember that's next to C double bond O,
So-
OCH.
So that would be this one. This one would be that CH3? Or the,
Actually, I think that would be the one around the 50, because it's directly bonded to an electronegative ion. Look at this down here, when you're looking at this. It's directly bonded to an oxygen, so that's going to shift it to this one here.
so then that means this CH3 is that one.
Uh-huh, exactly.
Okay.
And where's the CH2?
Right there.
Yeah, it's shifted a little more than normal for a CH2 because it's bonded to carbonyl, but those don't shift it nearly as much as being directly bonded to an oxygen.
So then number 2 would be that peak right there.
It would be. It's an ester, and so very good. How many of you got that? Okay. Kinda. All right. And that's exactly what we saw. Let's look at this work example. What approximate positions would you expect ethyl acrylate to show on a C13 NMR? Okay, oops. Oh, there's ethyl acrylate, okay. Well, you've already seen it. I can't seem to do it less. So let's just kind of think about it. Well, what are the things we have to take into account when we're looking at this one? Well, we have 2 that are in the double bond region, or the aromatic region, so that's going to be somewhere around 130, okay? We've got a carbonyl, but it's an ester carbonyl, so it's probably going to be less than 180 since it's an ester, but it's definitely not going to be over in the 190, 200 region. We've got this one next to electronegative oxygen, so it's going to be around 60 or so, and then this one was just primary, I'll be somewhere around 15, 20. Okay, everyone see how we kind of look at that? Okay. Sorry I didn't let you have a little bit more time working on that one. Just finished that one. Okay. The last major thing we're going to learn in this is called DEP. And DEP is very, very good at helping us determine things. It stands for distortionless enhancement by polarization transfer. No, you don't have to memorize that. It's called DEP though. And what it does is it changes pulse sequences and how it does it. And by doing that, it will actually separate different ones out. And we can use simple subtraction to determine if carbons are primary, second, tertiary, or quaternary. So first what we do is we take 3 different spectrums. The first one's just the normal broadband decoupled. Broadband decoupled, just a normal spectrum. Everyone got that? And that's going to show what? All the carbons. The second one is a DAP90. It only shows CHs. The third one shows CH3 and CHs as positive. And because this is only CHs, then we know what the CH3s are, right? CH2s are negative, and the quaternaries don't appear. So if it appears here and it doesn't appear here, we know it's a quaternary carbon. Okay? So this is pretty much what it's saying that we're going to do. Here's everything here. We can get our CHs from our DEP90. We'll get our CH3s really by our positive DEP135 because we'll subtract those off from here. And our CH2s will be negative. And if we subtract this from this, we'll get our quaternaries that way. So this is pretty much how it looks. Okay, so here's 6-methyl-5-heptene 2-ol. And when we're looking at it, we've got a double bond here, so we know that that's that, right? All right, now, when we're looking at that, what do we see? Is that a quaternary? In other words, are there any H's on that carbon? Notice that when we come here, we see it in the DEP90 as a CH, so that would be this one here, wouldn't it? But there's not this one here, so that must be this one here, right? This one must be it because it's not in either of these. Everyone kind of see that? Well, we've run out of time, so we'll pick it up here. I've got